A very good morning to the honorable panel of examiners and our supervisor Dr. Jalal. Today, we from Group 18 are going to present on our conceptual design about Group 3 base oil processing in lubricants manufacturing. My name is Shalini. Together with me today, I have my team members Yau Wen Zhen, Prakash Saravanan, Nur Nabila and Mohammad Taufiq. Before moving on to the presentation, I would like to present the overview. First, it will be the introduction of the project, followed by literature review, then a little bit on the PFD process, and then instrumentation and control strategy, safety and loss prevention, and finally the presentation will be ended with a small conclusion. Here is a little introduction to our project. Our project is based on Group 3 base oil. In the earlier days of the petroleum industry, it is said that the group with the highest saturation level and the highest viscosity index is considered suitable to process as a lubricant oil. Here you can see there are 5 groups in this table, and as you can see, Group 3 has a saturation level more than 90% and a viscosity index of more than 120. Group 3 base oil offer desirable performance in a wide range of attributes. Also, they are commonly mixed with additives and marketed as synthetic or semi-synthetic products. Examples are engine oil, the engine oil we use to service our car. There are two types, semi-synthetic and synthetic. Moving on, here are a few of the properties of Group 3 base oil. One of it has high viscosity index, which is more than 120. Next, it has excellent oxidation resistance, and also it has high thermal stability. Next, it produces low carbon residue, and it has a good biodegradable characteristic, which means it doesn't impact the environment. As we all know, the demand of base oil is increasing year by year. This is because the automobile industry and the oil and gas industry use base oil for various processes. Here we can see the demand is getting higher. It is important to us to design a plant that is highly profitable and produce a low cost byproduct gas that is also profitable. To design a plant, there are few challenges to overcome. The first one is to gain profit. This is one of the hardest challenge. Next is determining the plant capacity according to the market survey and economic analysis. Next, the plant location. Determining a plant location is really important. Every single element has to be taken into account. For example, raw material, transportation, utilities, and so on. Next, the design should also comply with the government rules, especially for the plant location and for the wastewater treatment plant. It is also important to maintain the safety when we are in the plant. These are the problem statements that we will face when designing a plant. Moving on, the objectives of this project. Although the main objective is to design a plant that is cost effective for Group 3 base oil, it is also important to consider other objectives as important. One of it is to perform processes by minimization of energy consumption to the extent of economically justified. Next is to design a safe plant according to the code of practice and industry guidance that also includes hazard studies. And next is to design a production plant with the compliance of environmental regulations. This is where we also take the wastewater plant regulation into consideration. The wastewater plant regulation comes under Department of Environment.
In Chapter 3, we are going to discuss on the process instrumentation and control. Instrumentation and control are very important and can be considered as the heart of any process plant to operate safely and efficiently. For the hydroprocessing reactor, we are using 3 feedback controller to maintain the inlet feed flow rate, to maintain the level of fluid in the reactor, and to maintain the temperature of fluid in the reactor. For ISO deviation, we are using 3 feedback controller also in order to maintain the inlet feed flow rate, to maintain the level of fluid in the reactor, and to maintain the temperature of fluid in the reactor. Meanwhile, for the heater, we are using cascade controller in order to maintain the outlet stream temperature. For mixer also, we are using cascade controller in order to maintain the level of liquid in the reactor. On this slide, we could see the piping and instrumentation drawing PNID, where we apply the control strategy into the equipment. For chapter 5, we are going to talk about the hazard and operability study hazard. Hazard is a formal procedure to identify hazard in a chemical process facility. The objective of a hazard study is to carry out a rigorous and systematic evaluation of process systems with respect to operational safety and potential hazard with foreseeable upsetting condition. And in our design, there are 3 study notes. The first study note is for the hydroprocessing reactor, second study note is for heater, and the last third note for the recycled gas from compressor. For note 1 hydroprocessing reactor, the parameters are flow and temperature. For less flow feed into the reactor, the possible causes are leakage of the reactor, valve partially closed, or flow rate indicator malfunction. The consequence will be less hydroprocessing reaction and less product yield. The action required is to install low flow alarm, install flow rate regulator, and do it regular inspection. For no flow of feed into the reactor, the possible cause are blockage of valve or bursting of pipe. The consequence will be no reaction and no product yield. Action required is to install flow monitoring orifice and do regular inspection. For more flow of feed into the reactor, the causes are valve fully open or flow rate indicator malfunction. The consequence will be reactor tank overload or reactor tank wall rupture. The action required is to install low flow alarm, install flow rate regulator, and do regular inspection. For low temperature of reactor, the possible cause are excess feed of overcooled liquid or temperature indicator malfunction. The consequence will be reduced product quality or risk of catalyst poisoning. The action required is to install low temperature alarm, install temperature regulator, and do inspection regularly. For high temperature of reactor, the causes will be excess feed of overheated liquid or temperature indicator malfunction. The consequence will be loss of hydrocarbon contaminant, catalyst deactivation, or loss production. The action required is to install high temperature alarm, install temperature regulator, and do regular inspection. For note to heater E101, the parameter is flow. Less flow of steam causing by leakage of the steam or flow rate indicator malfunction. Its consequence is targeted fluid underheating or reduced product quality. The action required is to install low steam flow alarm, install steam flow rate regulator, and do regular inspection. For note 3, recycle gas from compressor, the parameter is flow. For less flow of recycled gas, the possible cause are leakage of the recycled gas pipe or flow rate indicator malfunction. The consequences will be less hydroprocessing reaction or less product yield. Action required is to install recycled gas alarm, install recycled gas flow rate regulator, and do regular inspection. Second one is no flow of recycled gas. The possible causes is the compressor block. The consequence will be uncontrolled exhaustion reaction or compressor damage. The action required is to install recycled gas flow monitoring orifice and do regular inspection. For more flow of recycled gas, the possible causes are pump or compressor overpower or flow rate indicator malfunction. The consequence will be discharge high pressure or uncontrolled exhaustion. The action required is to install recycled gas alarm and flow rate regulator and do regular inspection.
Okay, for this wastewater treatment, from the facts, it is stated that from a processing plant of lubricants, if the plant operates by producing 105,000 drums per day, it will produce approximately 50 tons of oily sludge. So it is a very huge amount. And as you all know, all processing plant will have tons of wastewater. So for this kind of processing plants, the base oil waste streams that involved is sour water, processed water, as well as the sewerage water. So for the law and regulation that fall under these processing plants that involves covered for this processing plant is that normally we will use the Environmental Quality Act EQA 1974, but in this Environmental uh, Quality Act there are sub of regulations, but for this process plant we will only use the environmental quality regulations for industrial effluent. For the parameters that involve, that is very important is that the pH value, the biological oxygen demand, and also suspended solids. So other parameters, it is like if the company follow all the parameter is the best, but the most important thing that we want to see is these three parameters.
To treat the waste generated by our lube-based oil manufacturing plant, a separation technique by physical means, or more specifically via mechanical centrifugation, is proposed. Centrifugation is described as a mechanical process in which a centrifugal force field is applied onto a mixture to separate the components present in the mixture. The aforementioned components are separated according to density and/or particle size. The wastewater treatment method of the oil sludge is illustrated in this figure. According to the figure, the oil sludge is to undergo a pre-treatment step, where chemical agents, along with preheating via steam, are introduced to the oily sludge before it is sent to a centrifuge for mechanical centrifugation to take place. The sludge will then be stratified, where the upper layer, which consists of an oil-water emulsion, will be recovered, while the bottom layer sludge, comprising solid particle impurities, will require further disposal. The oil-water emulsion is then sent to a separator to recover the oil, while the separated water is recycled back into the centrifugation system. Further details pertaining to each process unit is explained next. During the pre-treatment process, chemical agents are added into the oily sludge, among which are demulsifiers, surfactants, or organic agents. The addition of these agents serves to reduce the viscosity of the oily sludge for ease of separation. It is also recommended that steam be used to preheat the sludge during pre-treatment process to further aid in viscosity reduction. It should be noted that pre-treatment not only eases separation, but also reduces energy consumption in the process. According to the principle of settlement via centrifugation means, the applied centrifugation force onto the oily sludge will result in the solid particles or impurities to move towards the bottom of the centrifuge system in the radial direction. In addition to doing so, centrifugation also allows for sludge dewatering to take place, where water is retrieved from the solid particles or impurities, which can be in large amounts, as much as 70% of the total weight of the sludge. The oil-water emulsion is then sent to a separator for oil recovery purposes, which can be achieved using a gravimetric separator. Gravity separation refers to an industrial method of separating two components that have significantly different densities. The recovered oil will be sent back to the base oil processing plant, while the water will be recycled back to the centrifugation system. That's all for the wastewater treatment method proposal. I will now pass the floor to the next speaker. Thank you.
Hi and good day. I'm Prakash, and right now I'll be presenting on the process economic and cost estimation of the lubricant-based oil plant. So some of the common assumptions that we have taken is that the plant has a lifetime of about 15 years, and it has a minimum attractive rate of return of about 15%. It also has an interest rate of about 7% for other economic calculations, and we are also using a currency conversion of Malaysian ringgit of 4.12 to every US dollar. And the operation time that we are estimating for our plant to run or to be operational is about 330 days. So if you could redirect your attention to the bottom left corner of the screen, you could see two indexes that we have highlighted over here. So the first correlation highlights how we could use a base cost or with a base capacity and scale it up to size our equipments based on whatever capacity that we are using, and we can account for different materials and different pressure ratings and also temperature rating by using the correction factors that are associated with this formula. Following that, we also have the next formula that accounts for the inflation rate and uses the index from year 2000 and also the index from year 2020. So these common indexes are available from Marshall and Swift and also from Chemical Engineering Index. Moving on, we have several categories of costs that we would like to highlight over here. First up is the capital cost. So for capital costs, this is the cost that one would have to put out upfront before they are earning any cost. So we have two types of capital costs. One is fixed capital cost and also the working capital cost. So fixed capital cost is primarily for the equipments and installation, getting the equipments and also all sort of stuffs. And the working capital is to begin operation. So in order to get catalysts, raw materials, your inventory and also the staff. So all of this are included into working capital costs. Now moving on to operating costs. In operating costs, we have about three categories. One is fixed operating costs. This is the labor. So you have supervision, labor, maintenance, and so on and so forth. And next up, we have the variable operating costs. This is where we have the raw materials, utilities, and so on. And finally, we have some general expenses associated with this, like administration and marketing. So from both of these, we could see that upfront, the capex cost is about 179 million, and our operating cost annually is about 3 billion. So when we look back at the revenue that we are generating for each year, we are generating about 17.8 billion every year. This is primarily due to the efficiency of the plant that we are able to cater such high products and such high volume. And the next thing that we have here is the depreciation. For here, we have accounted for 20% salvage value and had a straight line calculation for 15 years. And now let's move on to the analysis. We could see that the rate of return, ROR, and also the return of investment, ROI, are way beyond what one will normally expect. This is primarily due to the way we have designed our plant. We have utilized the capacity of an actual plant, but we have only included the costings of certain equipments that fulfill the scope of our project. So that is why we are seeing such huge margins of error, and this could be seen with the percentage error. For an actual project, the percentage error should be less than 25%. Ours has exceeded 25% and is up to 80%. And that could also be seen in our payback period, which is less than a year for a plant that has just begin commissioning. So I believe that is all from me. Thank you.
Alright, so my name is Mohammad Taufiq. So on this part, I will explain regarding my major part, which is the furnace. Okay, so let's proceed. So the design methodology in order to determine the furnace is that there is two part, which is the first part is by determining the furnace design, and the second part is the mechanical design. For the furnace design, we will determine the radiant zone of the heat absorption, and we will determine the total tubes length required, because from this total tube length required, we can determine the overall height of the furnace. For the mechanical design, we will determine the thickness for all the sections, which is the tube section, the convection section, and also the radiant section. And then we will also determine the dynamic wind pressure in order to look how the wind affected the furnace. So the basis of selection for this furnace is that this vertical fire heater is very cost effective and can reach higher power, and this furnace as well can provide high efficiency. So in every process plant, we always want to achieve high efficiency, so this fire heater is very suitable for this process. And then due to this vertical fire heater, the heat can distribute it evenly by placing the burner at the bottom. So here you can see the sample calculation. You can see the radiant efficiency, the maximum working pressure that we can calculate, then the dynamic wind pressure, and the last one is the dynamic wind pressure. So here is the specification data sheet. So at the head you can see the parameters of the streams that involved in this furnace, the inlet and outlet streams, as well as the data that had already been calculated during this uh, furnace design. So here you can see the drawing of this equipment. Uh, on top of left, you can see the cross-sectional view with the uh, internal diameter, and then on top of right, you can see the top view, including the outside diameter, inside diameter of the stack tube section, and also convection section.
Hi, my name is Yau Wen Zhen, and I will be presenting about the major equipment I worked on, which is the hydrocracking unit. For the hydrocracking reactor, we have decided to choose a packed bed catalytic reactor, more specifically a trickle bed reactor, to perform hydrocracking. It has a single-stage one-screw configuration because this particular configuration is known to be economical and can also produce Group 3 lube base oil very well. This is because the liquid flow in trickle bed reactors closely resembles that with a plug flow behavior, which would mean high conversion yields are able to be achieved. Moreover, there is ease of construction and operation since no moving parts are involved in trickle bed reactors, which also contributes to ease of maintenance and lower risk of damage to the reactor, along with lower setup costs. Pressure drops in trickle bed reactors are also reported to be low, which meant utilization of trickle bed reactors could lead to lower costs pertaining to pumping. Next, trickle bed reactors are flexible as they can operate at extreme conditions of high temperatures and pressures, while the packed catalysts minimize the possibility of catalyst loss. Last but not least, the catalyst beds in trickle bed reactor, unlike fluidized bed reactors, are rigid and do not settle at the bottom of the reactor. As a result, fouling and plugging of the reactor can be prevented, thus avoiding high maintenance costs. The operating conditions of the hydrocracking unit has been specified at 5.0 megapascal for pressure and 360 degrees for temperature. However, the maximum values for aforementioned parameters have been added with a 10% safety factor, meaning to say the maximum working pressure for the hydrocracking unit is at 5.5 megapascal, while the maximum working temperature would be 393 degrees Celsius. The catalyst used for hydrocracking processes must be bifunctioning, as they should be able to break and rearrange hydrocarbon chains, in addition to being able to add hydrogen to aromatics and olefins to produce naphthenes and alkanes. Zeolites, or more specifically ZSM5 with medium-sized pores, are used as catalyst support, as medium-sized pores offer higher activity compared to large pores, while also having a more efficient and orderly configuration of the adsorbed molecules compared to smaller pores. As for catalyst selection, nickel or molybdenum are potential catalysts. However, after some comparison, it is better to proceed with nickel for hydrogenation functions, as the pore volume of the catalyst remains almost the same as before impregnation, with a reduction of less than 20% compared to that of molybdenum, which is around 80%. Moreover, nickel and ZSM5 catalysts have surface areas 4 times higher than that of molybdenum and ZSM5. Moving on to the reactor dimensions. First, the volumetric flow rate is calculated by dividing the feed flow rate by the molar density. The volumetric flow rate is then used to calculate the catalyst bed volume, where the flow rate is divided by the liquid hourly space velocity, where its value has been taken from a patent found on Google Scholar. Next, the catalyst bed diameter has been calculated as well. The catalyst bed height, along with the reactor diameter, employ a slenderness ratio of 3, while the reactor height is calculated with additional spaces and height of closures in mind. Moving on to the mechanical design of the hydrocracking unit, where the thickness of the shell and subsequently the outer diameter of the reactor are calculated. A corrosion allowance of 2 mm has been assumed here. Here we have determined the thickness of the nozzle used. The functionality of flanges is to connect the pipes to various equipment and valves. Here we have calculated the thickness required for the flanges. Gaskets are mechanical seals which fill the space between two or more mating surfaces, generally to prevent leakage from or into the joint objects while under compression. In order to calculate the width of the gasket, certain information is required, such as the outer diameter of the reactor, along with inner and outer diameter of the gasket. The calculations performed previously are all inserted into this specification sheet. This is the drawing of the major equipment, the hydrocracking unit, along with its dimensions that have been calculated previously. For the cost of the equipment, it is calculated based on the given formula. Cost factors were obtained from textbooks, which stated that capital cost factor for carbon is 1.0. Capital cost factor for design pressure is 1.5, as the operating pressure of 5.0 megapascal is equivalent to 50 bar, which returns a value of 1.5 for cost factor. The design temperature of 360 degrees Celsius falls within the range of 300 to 500 degrees Celsius, which returns a correction value of 1.6, while cost indexes were obtained from online literature. With a base cost of $11,500 along with these factors and sizing, the cost of the hydrocracking unit has been found to be $175,362. Factoring in the currency conversion rate of $1 to 4.12 ringgit, the estimated cost for the hydrocracking unit is 722,494 ringgit and 25 cents. That's all for the hydrocracking unit. I will now pass the floor to the next speaker. Thank you.
Next, I'm going to explain on the process design of isodeoxane reactor R101. Moving on to the next slide. The first part I'm going to present is on the design methodology. Generally, the design methodology for the major equipment is classified into two major parts, which are process design and mechanical design. The overall design was carried out in 9 steps. First, selection of major equipment, isodeoxane reactor. Second, selection on type of reactor. We are going to use fluid packet bed. Third, we are going to determine the operating condition. Fourth, calculate the volume of reactor. Fifth, sizing of reactor. Sixth, reactor mechanical design. 7, reactor cost analysis. 8, technical drawing. And lastly, 9, description of reactor pre-startup, startup, and shutdown procedure. Next, we are going to talk on the basis of selection. The type of reactor we selected is fixed packet bed. There are 4 main reasons why we are choosing fixed packet bed. First is flow arrangement. In flow arrangement, the heat transfer, pressure drop, contacting phases, and regeneration of catalyst must be taken into consideration for reactor design. Isodeoxane process operates to allow more heat transfer and contact between catalyst particle and reactant. Second is high conversion. High conversion is required in order to reduce the undesirable side reactant from the unreacted feed. By using FBR, high conversion of reactant to product can be achieved as FBR offer the highest conversion per weight of catalyst. Third is lower capital and operability cost. As the required volume for packet bed catalytic reactor is smaller compared to fluidized bed reactor, the capital and operability cost will be low. And the last reason is catalyst loss reduced. By using FPR, there is low probability of catalyst loss at the catalyst in packet bed in the tube when it at contact with the reactant in packet bed catalytic reactor. In this slide, we can see the sample calculation. The first calculation that we done is volume of catalyst. Volume of catalyst is volume of flow inlet divided by LHSV. We are getting around 48.85 meter cube for the bed volume. We are multiplying the volume of catalyst with the void factor. We getting the bed volume is around 61.9 meter cubic, while for bed diameter we getting around 2.97 meter. For the bed length, using slenderness ratio 3 diameter equal to length, we getting the length is around 8.91 meter. For reactor length, we are going to assume that there are 10% of free space over bed at top and bottom for support catalyst bed. By multiplying with the bed length, we obtain 9.8 meter. The bed diameter using the slenderness ratio 3 diameter equal to length, we getting the 3 diameter is around 3.27 meter. While for the reactor volume, we get around 82.39 meter cube. For the height, we are going to assume that the height of closure is around 0.5 meter. From that, we are going to plus with the reactor length, we get around 10.8 meter. Next, we are going to calculate the minimum thickness for torus spherical head. By using the formula given, we obtain the thickness is around 23.37 mm. After that, we are going to calculate the total torus spherical head height. Using the formula given also, we get around 0.868 meter. Next, for the nozzle sizing, the first one is to find the optimum nozzle diameter using the formula given. We get for the inlet nozzle diameter is around 1612.39 mm, while the outlet nozzle is around 1612.41 mm. For the nozzle thickness, using the formula given, we obtain the thickness is 80 mm. In this slide, we could see the R101 specification sheet. In the data sheet, there are 3 data we could see, which are operating data, mechanical data, and catalyst data. in the operating data, we could see the operating temperature and pressure and design temperature and pressure. In the mechanical data, we could see the material that we are using, the thickness, the corrosion allowance, joint factor, and thickness of torus spherical head, stress, flange material, flange top, gasket material, gasket diameter, bolt, and nozzle thickness and diameter. And the third data we could see is catalyst. We could see the type of catalyst we are using is platinum slash zeolite sulfur 11. We can see also the weight of catalyst, which are around 22,351.88 kilogram. In the drawing, we could see the dimension of reactor, torus spherical head, nozzle inlet top view, and outlet top view. Thus, we could see that the inert ceramic balls are placed above and below the catalyst bed in order to distribute the feed uniformly and to prevent the catalyst from passing through. The purpose of using inert ceramic balls is to guard the bed from sudden pressure surge, as they can disturb the packing and cause maldistribution and bypassing of feed.
Designing the separator, there are few procedures to follow. First, we need to select the separator. Number 2, we need to select the type of separator. 3, we need to identify the optimum conditions of the separator and then determine the parameters when designing. Next, calculating the mechanical design and evaluate the cost equipment. So separators are used to separate the unconverted reactant from further purification, while the unconverted material is reused back to the reactor. The separation system can be classified as liquid and vapor separation. For this particular separator that I have designed, I have used two-phase separator. At the point when a reactor contains a blend of fluid and vapor, a phase separator such as flash column is normally used to separate the phases before entering the respective separation system, which is this separator is designed to be placed before the usage of the fractionator. This is the process design of the separator, where the parameters were gotten from HYSYS, whereas this is the operating conditions of the separator. These are the simple calculations I used to design the separator, where first I found the maximum allowable vapor velocity and then found the internal diameter of the mesh followed by the outer diameter, and then finally finding the vessel height. Once all the designs have been done and the data has been computed, this will be the finalized specification sheet for the separator of this plant design.
Thank you, Shalini. Hi everyone, I'm Prakash, and today I'll be presenting my major equipment, which is the fractionator. So if you can redirect your attention to the bottom left corner of the screen, here we have the simulated version of the fractionator, which is done in HYSYS. However, when it comes to translating it to the paper, we lack the technical or design data to perform such calculations. Thus, we have opted to go with the distillation column because of the abundance of design data available. So over here, we have opted to choose the LNG streams, light distillates, naphtha and kerosene to be the top stream and the base oil to be the bottom stream with a flow rate of 53,600 kilogram per hour and with a top stream of 120,000 kilogram per hour. When it comes to identifying the split between the components, because of the variety of components that we have within these streams, I was able to sequence the components according to the boiling point and find the point where it transitions from the top stream to the bottom stream, and from here we can identify that C14H10 and also C23H28 are the major components that are responsible for the split, and thus they could be attributed as our light key and also heavy key. Moving on. This is the minimum reflux ratio calculation, where we have the alpha I, the relative volatility, and our xid, which is the uh, composition of our components at the distillates, the top stream, and we have theta, which is a root, which I'll get back to you in a bit, and we have R main, which is the minimum reflux ratio. So the theta that occurs from this first equation is actually found through trial and error by using the second equation that is shown over here. Over here we use the relative volatility of every component, but at the same time we also use the composition in the feed stream, and here on the contrary to R mean, we are using Q. Q is basically the ratio of the bottom stream to the feed stream. So by doing that and experimenting the values, we are able to get a positive R mean value that should suffice. So in our situation, we are able to get a positive R mean value of 0.2 for a summation value of about 0.22. The error is significantly lower, but if we were to increase the R mean, the error gets greater. So thus we have opted for the R mean of 0.2. Next, we have the Fensky equation, which uses similarly the relative volatility and also the compositions of the light key and also the heavy key to calculate the minimum number of trays at maximum or total reflux. So some of the specification or the composition, their key values and also the relative volatility are specified in this table. Moving on. Upon calculating or computing our R mean value, we are able to calculate the R mean over R mean plus 1 ratio, and we could uh, select a reflux ratio that would suit our process needs. So in this case, the reflux ratio of 1.2 is chosen, and by interpolating it from the Urba-Maddox chart, we can get the N mean to N ratio, and by utilizing this ratio, we are able to compute 14 trays, and by using the correlation from O'Connell, we can get the efficiency of plate of about 43%, and by incorporating this, we are able to achieve 33 trays. However, one of these tray is represented by the reboiler. Thus, we have a total tray of 32. Next, we will be identifying the feed tray location using this equation. So here we have the correlation between the number of stages in the rectifying section and also the number of stages in the stripping section, and the values B and D represent the bottom and top streams in molar flow, and the other components, the compositions of the heavy key and light key in both the feed stream, bottom stream and also the distillate streams. Upon computing that, we are able to identify that the feed stream enters the tray at tray number 31. Aside from that, we are able to identify a few other important parameters um, throughout our design process. One of which is the weep point. Weep point seems to be a particularly important aspect, because since we are using a sieve tray and it has perforations within it, if we don't have sufficient vapor velocity, we would have weeping within the trays, and that would reduce the efficiency of our plate and reduce the separation that we are intending to do so. Thus, the actual vapor velocity must always exceed the minimum vapor velocity. And the way we can manipulate this is by manipulating our hole diameter or weir height, as they are the design variables to control weeping. Aside from this, some other specifications that I would like to highlight over here is that the column height is about 21 meters, and with a column diameter of 3.6 meters. The plate pressure drop is calculated to about 760 pascals, for each plate, and the total column weight is computed to be about 2,300 kilonewtons. For the enclosure, a toruspherical head enclosure is selected because we are operating under 10 bars. And finally, the costing. For the costing, we have obtained about 43 million. This is mainly because we are operating under pressure, so close to 4 bar. Thus, we have a thickness, wall thickness of about close to 70 mm. And since we are using stainless steel, thus the cost has ballooned to the amount that it has, as we could see now. So I believe that is all from me. Thank you a lot.